this activity is all about determinants. As a quick refresher, what is the determinant of a matrix? Well, first remember that a determinant is only defined for square matrices, and that's because square matrices can be thought of as representing linear transformations from Rn to Rn. What do I mean by that? Well, suppose we consider the square matrix 1, 2, 3, 4, multiplying A by some vector x, let's say -2, 3, will return a new vector in R2. So if this is our input to the linear transformation, the output is whatever I get by multiplying A by -2, 3, which in this case looks like 4, 6. So this is the output and this was the input. Okay, and when we work with square matrices, both the input and output, that is the vector you multiply the matrix by and the vector that comes out after you multiply the matrix by it, are living in the same universe. This was in R2 and this was in R2. Okay, and remember, the point of the determinant is that it gives us a way to measure how the volume of the enclosed column vectors, or the volume enclosed by the column vectors, changes through the linear transformation that the matrix describes. What do I mean by that? Well, let's consider this matrix in particular. The original standard basis vectors in R2, which I might call E1 for the first coordinate, so this is the vector 1, 0, and the next one, which I might call E2, which is the vector 0, 1, I can think of these two vectors as enclosing a square. I kind of drew it like a rectangle, but they enclose a square, and that square has an area of 1. Now, what happens when I transform both the vector 1, 0 and the vector 0, 1 using A? Well, the results will be the vectors AE1, which is just the first column of A. Notice if I multiply A by E1, it's saying take 1 of this column and 0 of this column. And the next one is the result of multiplying A by E2. So A times 0, 1 gives me just 2, 4. And so now the question is, what does the corresponding shape look like that is enclosed by AE1 and AE2? Well, if I draw my axes here, AE1 looks like 1, 3. So I might call this AE1. And AE2, let's pick a different color, 2, 4, it may look like that. That's this one. Okay? So what does the determinant of this matrix describe? It describes, well, its absolute value describes the area of this parallelogram. And in general, that's the name for this shape, the parallelogram. So the determinant of A, its absolute value, is this area. The reason we have an absolute value here is because the determinant may be positive or negative, and its sign depends on the order of the columns. So if I swapped these columns, or also swapped the rows, I would end up with the same absolute value of the determinant, but the sign would be different. Okay, so the area of this parallelogram, its absolute, that area is the absolute value of the determinant. So of course this isn't drawn to scale because this square looks bigger than this parallelogram, but the determinant of this matrix, as we will see, is -2, which means if we were to draw these to scale, this parallelogram would have double the area of this square.